Welcome to the Electrical and Electronic Engineering Lecture Series. Your anchor person is Professor Michael Sindinechi. Our topic today is Module 040, Statistical Analysis of Errors in Measurement. Please follow me in my lecture series by subscribing to my YouTube channel at https://youtube.com/@indinechimichaelc. Please like, share, and drop your comments in the comment section or reach out to me using my email addresses. You can also listen to my lectures on fundamentals of electronic instrumentation using the link given. Also, I would like you to visit Ebony Educational Consult website for more free online lectures in engineering at www.ebonyeducationalconsult.com. Today, like we said, our lectures will center on statistical analysis of error in measurements. Like we mentioned in our previous lecture on fundamentals of electronic instrumentation and measurement, we say that errors in measurements can be classified into three: as random errors, systematic errors, and human or gross errors. Now, we say that random errors are ones or those errors that vary in an unpredictable manner between successive readings of the same quantity. They vary both in the size of the error and on whether the error is positive or negative. Random error can be offset by increasing the number of readings and using statistical means in order to obtain the best approximation of the true value of the quantity under measurement. So today, we are going to look at this random error, which we said we can take care of using statistical means. So our lectures today is centering on determining the true values by statistical means. Now, statistical analysis of errors. So statistical methods can be used to find the most probable value and indicate the probable error with any one measurement. The most frequently used technique is to arrive at the probable value of a set of measurements of some quantities subject to random errors, and is the determination of the arithmetic mean. That is, you have to take so many records, different readings, and find the arithmetic mean. If you found the arithmetic mean, it gives you close to what the true value will be. But you are not going to stop at that. For you to get very close to what the real value is. So our lecture today is to progress from finding arithmetic mean to finding the deviations, mean deviations, standard deviations, and we will now treat some examples to show you how to do that. So, arithmetic mean is the sum of all the results x1, x2, x3 to xn divided by the number of results you have taken, which in our case we have labeled as n. So, for you to find the arithmetic mean of n number of readings, it will be the first reading plus the second reading plus the third reading until the nth reading. You sum it and divide by the number, which is n. So we say it is as shown in equation 1, x1 plus x2 plus x3 plus until xn over n, which is equal to summation x over n. We represent that as our equation 1. So the larger the number of readings, the more reliable the mean, and the more random errors are averaged out. So you see, for you to get closer to the true value of what your instrument is reading, you have to take repeated readings. And we say that the more you take these repeated readings and average them out, the better the results you are going to get. And to do that, you just use this equation 1 to find the arithmetic mean. Now, we move a bit further to find the deviation of the true value from the readings you have. So we say that the term deviation is defined as the amount by which an individual measurement departs from the mean. Thus, for a measurement of x1, the deviation will be equal to x1 minus the arithmetic mean, which is taken as x bar. Now, let us understand it very well. What we mean by deviation, we mean that you've taken readings x1 to xn. Now, what is the difference between x1 and the average, which is the arithmetic mean? What is the difference between x2 and the average, which is the arithmetic mean? And so on until you get to what is the difference between xn and the arithmetic mean. So as you do that, you now see that this deviation from the mean may have a positive or a negative value. Because if we take, for instance, the arithmetic mean is 10, while x1 is 9, then x1 minus the arithmetic mean, which is 10, will be minus 1. If, on the other hand, x1 is 12 and the arithmetic mean is 10, then x1 minus 10 will give positive number. So we say that this deviation from the mean may have a positive value or a negative value. So a measure of the spread of the result is then given by the term known as the mean deviation. Remember, we made two terms, arithmetic mean, deviation. Now we are meeting mean deviation. It's very important that you know these terms and how to find them. So this mean deviation is the mean of the deviations, and for the moment, ignoring the signs of each deviation. Remember, we said the mean can be, the deviation from the mean can be a positive or assume a negative value. So we're saying for you to do that, you have to ignore the sign, whether it is negative or positive, and make use of the absolute values. So we say that the mean deviation is equal to the absolute value of x1 minus x bar. We say that x bar is the arithmetic mean, plus x2 minus x bar, the absolute value of it, plus you continue until you get to the absolute value of xn minus x bar. So when you write, a term and use these two lines to enclose it, it means that you are looking at the absolute value, irrespective of whether it is a minus or a plus, whether it is positive or negative. You are just taking the absolute value. So that's, if we sum that, it gives us what is contained in equation 2, which is that the mean deviation is equal to summation of all the absolute values from x1 to xn minus x bar all over n. We say where the xn minus x bar enclosed in two parallel lines is the absolute value irrespective of the sign. So we say here, you have to note that the smaller the mean deviation, the greater the precision of the instrument. The smaller the mean deviation, the greater the precision of the instrument. In our previous lecture, we have defined what precision is. So, a more useful measure of the spread of results is the standard deviation, or what is known as the root mean square deviation. So we come to another term now, which we call the standard deviation or the root mean square deviation. The sum of the squared deviations for all the measurements obtained divided by the number of measurements taken gives you the mean of the squares of the deviation. The root square of this quantity is the root mean square deviation or standard deviation, giving us sigma equals square root of the values of x1 minus x bar squared plus x2 minus x bar squared plus continue until you get to xn minus x bar squared, which will give you that sigma is square root of summation xn minus x bar all squared all over n. We call it equation 3. Now, at this point, it is important for us to know from equation 2, we were making use of the absolute values. In equation 3, that absolute values, which is the two parallel lines that has, something enclosed inside, has given way to using brackets. So I want you to tell me in the comment section why we have replaced that absolute values with bracket, that is xn minus x bar in bracket squared. It is very important that you know why we have, made that change. If you don't know, say in the comment section, I will put you through. If you know, also say it in the comment section. The mean value of a set of readings is more likely to be close to the true mean if the number of readings in the set is large and the spread of results very small. I want you to understand exactly what we are doing here. We are looking at instrumentation and measurement. And we have defined instrument as that device that helps you to measure true value. So if you measure only once, you may not have the correct result. So we say that it is good for you to take so many repeated measurements and then find the arithmetic mean, find the mean deviation, find the standard deviation, and if the number of readings are more, then you are likely, when you find the mean value, to be closer to the real result of the readings you have taken. So the closeness thus depends on the number of readings n in the set and the standard deviation of the set of the readings you have taken. It is represented by what is termed the standard error of the mean, given as alpha, where alpha is equal to sigma over square root of n. So with this, you can compute all the errors arising from your, taking different readings. Now, let's see how example 1 can get us, closer to understanding what we are saying. Say example 1, a set of independent current measurements taken by 4 observers was recorded as 117.02 ampere, 117.11 ampere, 117.08 ampere, and 117.09 amps. So it says calculate A, the average current, and B, the range of error. From our equation 1, we know that the average current will be calculated using I average equals I1 plus I2 plus I3 plus I4, all over the number of readings. In this our case, the number of readings is 4. So the I average will be the figures 117.02 plus 117.11 plus 117.08 plus 117.03 divided by 4. That gives us 117.06. That becomes our arithmetic mean. When we say mean, is the same thing as taking the average. So the second question says, what is the range of errors? Then the range of errors is looking at those readings, which one is the highest one? The highest one is 117.11 amps minus this I average, which gives you 0.05 amps. Now, the range of error, looking at the lower range, will be the I average minus the I minimum. The I minimum in the readings is 117.02 amps. So the range of error at the lower level or lower threshold is I average, which is 117.06 amps minus 117.02 amps, which is the minimum. It gives you 0.04 amps. Therefore, the range of error will be the error at the maximum side and error at the minimum side divided by 2, which is 0.05 plus 0.04 divided by 2. So you see that you will now have your answer in the lower side minus, in the upper side minus. So your answer becomes plus or minus 0.045 amps as your range of error. So as simple as that. Let's look at another example. Example 2, it says the following results were obtained from measurements of a voltmeter: 99.1 volts, 99.0 volts, 99.4 volts, 98.7 volts, 98.8 volts, 99.0 volts. Now the question is, what is the arithmetic mean? Just like before, you add all of them and divided by the number, which is 6. That will give you 99.0. So that becomes the arithmetic mean. But go further to now find the mean deviation from the mean. So the mean deviation from the mean is now taking the absolute values of x1 minus x bar, x2 minus x bar, and so on. So that gives us 99.1 minus 99.0. Then the second one, which is 99.0 minus 99.0, which is 0. You do that at the end. If you get something, you divide it by 6, it gives you 0.17. So from the question, it says find the arithmetic mean. We found arithmetic mean to be 99.0 and the mean deviation to be 0.17 volts. So the answer is there. The arithmetic mean is 99.0 volts, while the mean deviation is 0.17 volts. So the question can go on to ask you to find the standard deviation. So you continue with the equation 3. Now, we have another example. That example here is the current passing through a resistor that have a value 100 plus or minus 0.2 ohms is 2.00 plus or minus 0.01 amps. So calculate the limiting error in the computed value of power dissipation using the relationship P equals I square R. Again, we express the guaranteed limits of both current and resistance in percentages instead of units. Now, we are told that I is equal to 2.00 plus or minus 0.01 amps. But we know that 0.01 of 2.00 is equal to 0.5%. That is 0.01 over 2 times 100 over 1 will give you 0.5%. Therefore, we move the limiting error in each percentage to give us that I is equal to 2.00 plus or minus 5%. Again, we do the same thing for the resistor or the value of the resistance, which is R equals 100 plus or minus 0.2 ohms. If we do the same thing, you see that 0.2 of 100 is equivalent to 0.2%. Therefore, the resistance is equal to 100 plus or minus 0.2%. Now, if we use the worst possible combination of errors that can be displayed in the power rating of that equipment, then the limiting error in the power dissipation will be from the formula given to us, P equals I square R, which is 2 times 0.5% plus 0.2%. We want you to get it right. The limiting error for the current is 0.5%. But because it is I squared, that is, you have two I's. You have two units of the current. So it becomes 2 times 0.5% plus that of the resistance R, which is 0.2%. So you add them, it will give you 1.2%. Therefore, the power dissipated should be written as P equals I square R, which is 2.00 squared times 100. That gives you 400 watts, plus or minus the limiting error, which is 1.2%. Now, what is 1.2% of 400? That is 4.8. So the power in the system will be 400 plus or minus 4.8 watts. This means that the power dissipated in the resistor lies between 400 minus 4.8, which is 395.2 watts, and 400 plus 4.8 watts, which is 404.8 watts. So you see that you are now having a range that between 395.2 watts and 404.8 watts, anything there is acceptable by this measurement based on the tolerance of plus or minus given in the equation. So with these three examples, we believe that you can handle any computation in errors rising from measurements you have taken. So quickly, you take these exercises home, do them, supply your answer in the comment section. I will usually go through the comment section and correct you if you are not correct, and confirm when you are correct, and if there is error, help you to put you through. So exercise 1, it said a 0 to 100 voltmeter, that is a voltmeter that measures from 0 to 100 volts, has 200 scale divisions, which can be read to half division. It says, determine the resolution of the meter in volts. It's very simple, but we want you to reason it out, that this can read from 0 to 100 volts. And if you look at it, it has 200 scale divisions. So it says, what can be read to half which can be read to half division? So determine the resolution of the meter in volts. In our previous lecture, we have defined what resolution of an instrument is. So use it to reason out this exercise 1. You may not have to write anything down to answer that question. So 2 says, repeated measurements of a capacitance using a bridge gave the following results: 8.0 microfarad, 8.1 microfarad, 8.3 microfarad, 7.9 microfarad, 8.2 microfarad, 8.4 microfarad, 8.1 microfarad. Now, it says, compute the arithmetic mean, B, the standard deviation of the results from that mean, and um, exercise 3, the measurement of a resistance over a period of time gave the following results in ohms: 10.16 ohms, 10.15 ohms, 10.14 ohms, 10.05 ohms, 10 ohms, 9.99 ohms. Says, what is the arithmetic mean? What is the arithmetic deviation? What is the standard deviation for the resistance over that period of time? So drop your answers in the comment section, which I will look at and correct as necessary. So thank you for listening, but we want you to join in the next lecture, which will be now looking at a typical digital electronic meters that can help you now to make readings in your instrumentation. Yes, there are, analog ones, but they are no more in vogue like that. So we will not waste our time on analog meters. We will go straight to digital electronic meters. So join me in the next lecture. Subscribe to my channel so that you will have notification on when that lecture on digital electronic meters will take place. Thank you for listening.